So again, a non-centralized algorithm is needed if sorted list is not sufficient. And a bigger problem here is that we can have different consensus states. I didn't show that in my example because I would have had to put breakpoint down in the multicasting code. But we want to avoid this problem also. Okay? And the key was that we can use the voice of more than one member. And we said if we use only one member, that member might die. So we want to use the voice of multiple members. And we want to go from, so the problem is how to detect and sequence concurrent requests. That's the problem. And we want to go from a very hierarchical, centralized system to a majority-based or parliamentary system. Okay? And I'm using the word parliamentary to motivate the algorithm I've been talking about, and hopefully you've been waiting for. It's called Paxos. Paxos is a location in Greece which had a fictional consensus system. And how many of you guys have heard of Leslie Lamport? How many of you have heard of a Turing Award? You know anyone who's got a Turing Award? Fred Brooks. We are in his room. So Leslie Lamport is also a Turing Award winner. Brilliant guy. And like Fred, extremely good speaker. So he gave a distinguished talk, in fact, at UNC. And I've seen many theory talks, and I think that stood out the most. That was the clearest talk I've seen. And what was interesting was that he just had a slideshow essentially. Every line was a new slide. And I think this might have been in the time when we actually had slides. But I learned a lot from the way he presented things. Okay, so we're going to talk about Paxos. And what you learn from this slide is that Paxos is something that needs simplification. Okay, and yet, so Paxos actually, so Lamport wrote he did the first paper. Actually, from what I believe the history is, and I'm not 100% sure, that this algorithm was invented in the late 80s by both Leslie Lamport and Barbara Liskov, who's another Turing Award winner at MIT. And they both came up with it independently. I think I read it somewhere, but I'm not 100% sure. But it was written up in 1998 by Leslie Lamport. And then he wrote this paper saying, he says, look, whenever I go to conferences, theory conferences, people say it's too complex. So let me make things more clear by removing all the Greek symbols and just talking plain English. Okay. So it's the simplest and most obvious of distributed algorithm according to him. But we'll see. Okay. And I'll put a lot of simplifying editorial comments. So hopefully they're correct based on my understanding. But the algorithm did make my head spin. Okay, so that's the question. How to detect and sequence concurrent requests. Okay. And a single replica decides in the centralized case. Now, multiple processes decide. Okay. Multiple acceptors decide. So we have the same scheme that we had in synchronous system and the centralized system. Proposers, acceptors, and learners. Okay, learners learn, so they are not active in making decisions. Okay, so proposers may be one or two. The acceptors are the ones that are a set. So now a set decides rather than an individual. And this is not too crazy. After all, when it comes to service denial, the set is deciding, right? We might take the majority value, we might take an individual value. So why not let the concurrency control also be decided by majority or by the set? Okay. So they already decide site-specific aspects of feedback in synchronous case. Okay, when they're synchronous, we poll them. So why not? And by the way, asynchronous case will not make sense here. We're going to go from 2 phases to 3 phases ultimately. So if we have all these phases, we get synchrony for free. So why not get it since we have all these rounds? Okay. Okay. So our centralized algorithm looks like this. Okay, the central guy sends accept requests, which are purple, gets back accept responses, which are red, and based on the responses it gets, it goes and sends green learns to the learners. And how would this architecture change now based on what I said earlier?
So like the red arrows.
Yeah, you're on the right track. The red arrows.
It isn't going to the central. It's going to like the rest of the. It sounds weird, but it should go to the rest of the acceptance, or like some set which decides on the verdict.
Okay, so I think what you're saying is right. That it should go to some set, but it should go to some set for what reason? So that the set can decide whether the value is consensus or not, right?
Yeah.
So that means they are learners. Whoever needs to know the consensus value should go to them, right?
So you mean like go straight down to?
Go straight down. Whoever needs to learn the value learns what everybody's accepted.
So does that mean your centralized block? So the blue block is essentially for serialized ability and it doesn't do anything.
Yeah, the serializability is being done by distributedly by the. No, we're going to get rid of the central guy. I'm saying, how does the picture change? First, we get rid of the central guy, for sure. Once we get rid of the central guy, we need to take those arrows that were going to him and put them somewhere else. Yeah.
I mean, we need to connect up all the acceptors, obviously.
We need to connect up all the acceptors. We basically are saying that every acceptor individually makes a decision. Then we have to, whoever needs to know the decision has to go and add up the decision somehow. And whoever needs to know the decision is a learner. As it turns out, our acceptor, learner, and proposer set will be all the same. But conceptually, if we have separation, whatever algorithm the acceptors are going to use to accept the aggregate value can be used by the learners directly. Right? So let me show you the picture. We get rid of the central guy. So and we get rid of the client guys, then and we have to now get rid of the central guy. So we take all these arrows that were going to the central guy and put them to the learners directly. Okay? So now the circle that remains is a proposer. No central guy. He's just the direct proposer. He proposes to all the acceptors. Each acceptor makes a decision. They send the decisions to everybody who needs to know what the aggregate decision is. And the ones who need to know are the learners. They all aggregate in the same way to hopefully reach the same consensus value.
So it's like the learner is going to say, so like in this case, the learner is going to say, I have 3 messages from the acceptors. I got 2 success. So I'm going to take it and change my value.
So something like that. The learner can look at the majority value and say, okay, I'll just pick the majority value. Yeah.
So how do the learners learn about the other learners?
So we have to make sure that the learners all execute the same algorithm or execute a consistent algorithm.
Oh, no, I meant like the...
How do they know who the other learners are?
Yeah, because they have to send them to the other one, right? Like
Okay, no.
are the learners.
So the picture that I've shown here,
It just says its own value.
they just learn their own value. Now we don't have this intermediary that goes and makes a decision and sends a message to the learners.
Okay.
The learners have become more active now. They're not just pure learners.
Yeah, no, I think we're on a different page. So I think I understand what you're saying, but so a learner sends to an acceptor.
No. The red lines go from acceptors to learners. So what your question was, how does the acceptors know who the learners are? Right? Because your question was, how do they know? Yeah, everybody knows about everybody else. Let's put it for now. That's a simplifying assumption. The real assumption is the proposers know all the acceptors, and the acceptors know all the learners.
Okay. My question was like, how do they know those?
Yeah, so think of a real situation. We've got slaves and mirrors. The master knows all the mirrors, all the slaves, and the masters and slaves know all the mirrors. They just, that's something has to be hardwired. Or you could go to some session directory and find out who they are. Okay, so that's what happens in my implementation. They all go to a session server, and they go and register themselves, and the session server tells everybody about each other, and hopefully it doesn't die, and that's how they know each other. And if not, they could have IP addresses. Yeah.
Yeah, so like just from the architecture, so like you said the proposer and the acceptors and the learners can be the same set. So
Yes.
in that case, would it would just be like one process with 3 threads, and then one thread for propose, one thread for accept, and one thread for learners.
You're saying in implementation, they'll have 3 different threads.
Yeah.
As it turns out, in my implementation, all remote requests are executed with the same RPC thread. So as it turns out, they're all done in one thread. All the remote calls are done in one thread. The proposing calls are done in a separate thread.
So you handle all the RPC to ensure a serializability? Or
Okay, so you're saying how do you ensure serializability? So that's the problem.
yeah.
We have to make sure that the concurrency control algorithms work consistently, so that they all accept the same proposal and reject the other ones.
Yeah, also handle concurrent changes. Like if 2 eligible values come in sort of concurrently, how we
In the same process, if 2 values come concurrently in the same process, or
yeah,
or in different processes.
I think different questions.
Yeah, so that's the question.
Yeah.
Okay, that is the problem we're trying to solve.
Okay.
If 2 proposals come in at the same time, I don't show 2 proposals here. Okay, but in general there can be 2 proposals. There was just going to be too many lines then. So if 2 proposals come in, the acceptors have to decide which proposal's value wins. That's the problem.
Yeah, but if they're both eligible, so like 42 and 44.
Yeah, if they're both, so in fact in the algorithm I'm going to talk about, the service denial, just forget about it now. Assume they're all eligible.
Okay.
Okay? The question is, which one do we choose?
Yeah.
Right? That's exactly the problem we're trying to solve.
Okay.
Okay? And the partial solution to it that I'm giving here is that the acceptors make the decision individually. Okay? And then the decisions get accumulated and learned by the learners. Okay? Now, there's a lot of things that I'm not telling you. But architecturally, this is what's going on. Algorithmically, I haven't told you what's going on. Okay? But you kind of already hinted at majority. Okay? So let's go. Okay, so let's before we go further, let's go and see what our assumptions are, what guarantees we want to give. If we're using TCP/IP, we can assume that they'll be in order, but the algorithm I'm going to talk about allows things to be out of order because it has proposal numbers. And so far, we were not doing anything with proposal numbers. We were just printing them out for debugging reasons. Now, proposal numbers will be used to order messages. And so we can assume, in fact, that we don't have TCP/IP. We can just UDP. Okay. We will assume in this algorithm that it is a write once value. It's like a final constant almost. That we have to go and initialize the variable once, and it'll never be reinitialized again, reset again. Okay. And if you want the more complex thing, I don't have time to get into that, but that involves it involves composing what I'm going to talk about, and I'll talk a little bit about that soon. Okay, so for now the value is written once. Okay, and the idea is that you're sending commands to a state machine. All the state machines are executing those commands, and the commands in fact will be read also once. And we are trying to just figure out the value of a particular command in a sequence. What should be command number 4? Okay. There's a typo here. If a value commits at a learner, okay, it'll commit, the same value will commit at another learner also. Okay. So all committed values at the learners will be the same value, will be equal. a value may not commit at a learner depending on what kind of failure has occurred. Okay, so it's what we wanted, right? It's either pending or it's the same. Okay, so it will be either pending or it will be an agreed upon value at the learners. Okay, and we'll see that a learner will commit to this value when it receives a majority vote from the acceptors, and if it doesn't receive majority vote, if there's network disconnection or whatever, then it just won't commit. Okay, and the algorithm assumes that ultimately messages can be retransmitted and machines can come back up, and given enough time, everything will achieve consensus. Okay. Okay. So the right once is the key idea here. I mean, key point here is what distinguishes this algorithm from everything else we've seen so far. Okay, and because things are so complex that even doing this part is hard. Okay. So let's go and try to figure out what our acceptor algorithm is going to be, and what a learner algorithm is going to be. Okay. Now, what did our central sequencer do? Our central sequencer accepted the very first value it got, right? And it rejected the other values. Each acceptor could act like a central sequencer and accept only the first value it got and say all other values are pending. Okay? And the learner does exactly what I talked about earlier. The learner picks the majority acceptance. So the learner does not wait for responses from everybody. The learner gets responses, only waits for responses from the majority. Okay? And will that guarantee consensus? Because different learners could use different majorities, depending on how they're connected. So, would the learners, would the learners agree to the same value?
If you have 3 or more values, it's possible you could never reach consensus, or you could never reach a majority.
Okay, so that's a very good point. We'll get to that. Assume for now that we have majority. If we have majority, can we? Are all majorities going to have the same value? Given any pair of majorities, will the two majorities have the same value?
We got your values from, I guess?
No, I mean there are 5 nodes. 3 is a majority, right? So if one majority says the value is 42, is it possible that another majority says the value is 29, assuming that they are not equal, the sets are not equal? It's not possible? You can't have 2 majorities. Well, I can have a majority consists of set 1, 3 and 5 and 2, 1, 2 and 3. So 1, 3 and
Okay, well, if the sets are mutually exclusive, you can't have 2 majorities.
Are we talking about majorities or pluralities? Because
majority.
Okay, because majority means more than 50%.
Yeah, more than 50%.
Okay.
So 2 majorities can be different sets. We agree on that?
Yeah.
But will the value accepted by the 2 sets be the same?
Yes.
Because?
Obviously, if a majority is accepting the value, that has to be the same. The sets can be different. Like 1, 3, and 5 is different than 1, 2, and 3. But if all of them have the same value, that's the only way for both to be a majority.
But do we enforce until like the acceptor will not be? No.
No, I mean, you're saying it I mean, the answer is that yes, you guys are on the right track, but I'm not sure I get the argument here. Majority means that, the majority of members agreed to the value. Okay, so 1, 3, and 5 agreed on the same value. Then we have another majority with a different set, and those members agreed on the same value. Two majorities have to have at least one member in common. So they have to have the same value. Okay? So different acceptors can get proposals in different order. So there are ordering issues. Acceptance may arrive in learners in different orders. So different learners may have different majorities. Okay? But each pair of majority will have at least one member in common. We'll select the same proposal. Okay? So now we have to deal with match problem. Two proposals may get the same number of votes. Okay? So we can have an odd number of acceptors. And Matt, what were you saying? That won't work?
Well, if you have three different values, it's possible that none have a majority, none have more than 50% that are accepted.
In fact, if you have n acceptors, it's supposed to have n concurrent proposals, each of which gets one acceptor. Okay? So that is the problem we are going to solve. So far, everything has been great. If we had a majority, we are beautiful. The trouble is we can't guarantee a majority. So that is the key problem in this whole scheme. Okay. So what we will do is, how to break ties, right? We can break ties based on when a request occurred, time. What else can what else can be the basis for breaking a tie? And we already saw that when we were trying to figure out which should be the next coordinator.
These have rules for if there is a tie, then you break it this way.
Yeah, based on, it's got proposal numbers.
Yes, sorted by proposal numbers.
So as long as each proposal has a different number, whichever proposal number is the highest, let's say, or the lowest, it'll accept a picks.
So it works fine as long as you have a rule that they all agree.
Yeah. No, so as long as they have a rule, there's a rule they all agree to. That's called non-Byzantine failure. There's Byzantine failure also, where there are some traitor generals who are not following the rules. Okay, so when I studied distributed algorithms, we spent all our time on non-Byzantine because those are the complex Byzantine algorithms. Those are the complex. There are fantastic bounds there that you can prove. Our lower bounds you can prove. So, but we are talking of non-Byzantine failure detection. So they all follow the same rules. Okay. So each acceptor accepts a proposal with the highest proposal number it will ever see. Right? Sounds good? We're going to be here a little while, guys. So it will ever see.
Well, it's time and you'll eventually see a higher number, right?
Or not.
Or not.
We don't know. We are going to set the value only once. Okay? And we don't know when, if we will ever receive the highest proposal number. And we certainly don't know. We can't predict the future. So when you can't,
Would there be a disadvantage of using the lowest proposal number? Like for the last?
Highest or lowest is symmetric. Okay? It's symmetric. Either way, it's got to figure out, which one it is. Which one is the lowest? Because the proposal numbers are being chosen by the proposers. And the proposal numbers are not in sequence as if it's not. And this is the first. Remember, we're setting the value only once. So we don't know, which is going to be the lowest one, or whether the lowest one. If we say, oh, okay, they all start from 1, it doesn't know whether 1 will ever be received or not. Okay?
So are we going to use a clock now?
No, we're not going to. We're going to use a clock ultimately. Ultimately, we're going to use the clock, timeout at least, but not a global clock. So what do? Well, we can't look in the future, but we can. So we can. It's like somebody says, pick the best employee you'll ever get, and you don't know you'll ever get the employee. So what do people do? Well, some people just say we're going to pick the first employee and not change our mind. Okay. Some people who are more go-getters will say, okay, we'll pick, fire, hire, fire, and so forth.
Well, at least in the employee case, I feel like most people have some sort of threshold, and then once that threshold has been released, and they just pull the trigger and just go for it.
So in the case of employee, we use some kind of semantics that these are the qualities we want. Right now, the only quality we care about is concurrency control. We're not even judging whether the number is even or odd. And so we're just trying to make sure that we have a consensus. And we can't go and say that we will, look at the quality of the value. Yeah.
You just say the poll's closing at some point. Like you might pick the highest.
Now you're coming to a synchronous, time-based algorithm.
Can't do costs.
So, and the trouble is that you may supposing you give them 2 days, and all the votes occur in the first minute. You have to wait for 2 days to get the vote. And imagine a transaction system that's having so many uploads of videos in Facebook, right? So we're going to use proposal numbers to break ties, but we can't predict the future, so we will keep changing our mind. Okay? So an acceptor will be allowed to accept more than one value. Okay?
Okay.
I told you this makes your head.
What?
Can you remind us, how is it that an acceptor decides whether something's, acceptable?
How does the acceptor decide whether something is acceptable or not? Exactly. My first criteria was it decides whether it's the very first value is received. That didn't work because there'll be no majority. Now it decides, is the value that has been proposed, does it have a higher proposal number than the one I've already seen before? If it has, I'll accept its value, else I'll reject it. The idea is that all the acceptors will converge to the same values. If we let enough time go, they'll all converge to the same values, and we can get consensus.
So now we're just forwarding whatever we see.
Yeah, we're still forwarding everything we're seeing, and it's getting more and more. I told you it made my head spin, and it's not as obvious and simple as we mere mortals see things a little differently from Lamport. So, but still, it's making sense, right? That we are just going to hire and fire, and we're going to now hire somebody who has a higher proposal number, and that's the only criteria we use. Okay? The problem is that the learners have to agree on the same value. Each individual acceptor is changing their mind, but the learned value better be the same. That's the challenge. That's what makes this algorithm so interesting and complex also. Okay? So cannot predict future. So each acceptor accepts a proposal if it has the highest proposal number it has seen so far. Okay, I forgot the if here. And a learner picks the value that has majority acceptances. Okay. So individual votes are changing. The question is the collective vote changing? Is it possible that we learn one value and then we learn another value afterwards? Yeah, you're all saying yes. Right? And acceptor can change his mind. These proposals might come in series. First proposal number 1 comes, everybody accepts. It's learned. Then proposal number 2 arrives. Everybody accepts it. And so the values just keep changing. So nice try, but not quite there.
So in terms of learners, is it first.
Okay.
Like,
So now that multiple values can be learned, the question is what can we do in the system to make sure only one value is learned? And one thing we can do is control what the learners do.
Yeah.
Okay? So, this is not something that Lamport suggests as an alternative, but this is something that I consider in this talk, and I'm glad this is something that you consider too. So a learner picks the first value that has majority acceptances. Will we all converge to the same value? For the same reason we talked about earlier, that two majorities have at least one member in common. It will certainly solve the problem I talked about earlier, that these things are coming in phases. First proposal number 1 comes, it's accepted, then the proposal 2 arrives, and we say, we've already accepted 1, so we're not going to do 2. Yeah.
Okay, so it's the problem now knowing when to start accepting again?
Okay, we will never accept again. That is a very big problem, by the way.
Except one. So that,
But that is exactly it. I mean, that is the reason why I can't really create a very practical assignment for you guys. And in your assignment, what we will do is, we will just have one proposer, because we're going to run those experiments, and we'll simplify the algorithm so that all the messages that have to be sent still get sent, so that you can go and time it, but it can still be made to work. So it will not exactly be the algorithm, but it will be a modification, because that is a extremely important problem. So does the argument really hold true that if two majorities have an overlapping member, then they will have the same result?
if messages are assumed to be sent in order, then yes.
You can assume messages are in order, yeah.
So if you have two majorities, one of them is earlier, and one of them is later and more preferable, and the overlapping members will choose the later one, and it'll converge over to the later one.
So the overlapping members can change their mind. And they were with one group earlier, now they're with another group. And we have two different values. If they're opportunistic, we can't decide. So that's a problem. An acceptor can change its mind. Okay? So different learners can get different majorities. Common members may have changed their mind. So different learners can pick different values. So it doesn't work. But, nice try again. We are trying to control what happens. And our idea was that we control what the learners do. So we won't control what the learners do. We won't control what the acceptors do. We will control what the proposers do. Put some constraints on them. And thereby hopefully converge. Okay? So what do you think intuitively we could make the proposers do to make sure that we don't? Yeah.
So when you propose, you make sure the proposal number is monotonically increasing.
Okay. So what you're saying is that the proposers can make sure that the proposal numbers monotonically increase. This monotonically increasing stuff is useful when we are going to change a value multiple times. Here we change the value only once. Okay? So that's not going to help us very much. Yeah.
The proposer doesn't make another proposal until the learners have actually accepted a value.
The proposer doesn't make another proposal unless the learners have accepted a value. The proposer, how does it know whether there's another proposal or not? That's a good point. So far, we never had a proposer figured out whether there's no central guy. So somehow you're saying the proposer should know about what's happened before.
Yeah.
That is the key. That is the key. You can't get away from that. Lamport says this algorithm follows from the natural properties of distributed systems. or follows, it doesn't use the word natural, but it follows from the properties of distributed systems. And we're kind of seeing that. There's not much else we can do. We have so few choices that we're being constrained to go the same path. So we really have to control the proposer. That means before proposing, the proposer has to know what the global state is. It can't go to a central proposer, so it has to go to all the acceptors. So the algorithm is not two phases, okay, where you have three phases. The propose is now two phases, and then there's a separate learn phase. Okay?
So the proposal is going to have to ask the learners first? Or
The learners learn what acceptors have told it. They've told them.
It asks the acceptors.
It asks the acceptors. So we're getting to where we want. Majority is good. We want to use sequence numbers to converge to a value. That's all good ideas. On their own, they're not enough, but together they're going to be good. And now we've got another good idea, that the proposers query what's happened earlier. Okay? So a proposer does not override consensus achieved from earlier proposal. A new proposal does not override something that's been learned from the earlier proposal. That is going to be one of our properties. Okay? So proposer needs to know distributed state before proposing. Yeah.
So the proposer queries the acceptors to figure out if that current proposal has a majority, and if it does, it doesn't allow it to override.
Okay, so what you're saying is the proposer figures out whether the proposer queries the acceptors to figure out whether there's a majority or not, and there's a majority, it doesn't go and propose a new value. That might be one condition it uses.
No, he's asking, like, what's going on.
Yeah, I don't know.
Oh.
All I know is it's got to do some querying. It has to query the proposed acceptors. We agree on that. What that form of query is, I don't know. We will let it follow from the natural properties of distributed systems. Okay? And I'm not saying this sarcastically. I mean, I think he's right. You guys are converging to it on your own. And, I mean, if you go on the web and people think this is a very complicated algorithm, the fact that you've gotten so far inductively, this is my challenge. My dream was I could present it in an inductive fashion. Most people will present it in a deductive fashion where they just say, here's the algorithm, here's what it works, and let's look at the cases. What I'm trying to do is derive it from what we already know, synchronous, asynchronous, two-phase, and I'm happy that you guys are filling in the blanks the way it should be done. Okay? So, proposer needs to know distributed state before processing. What that state is, we don't know. But we know it's got to know something about what's happened in the past. And it's got to use the state in some way. And what Matt said may be exactly what we want. We'll have to debate whether that's enough or not. Okay? So what it will go and figure out is ask each proposer, so what do you think I'm saying here, or what do you think, what state can it get from the acceptors?
Yeah, just
The last proposal that the acceptor has seen, knows about, and the last proposal it has accepted. These are two different things. What does it know about, and what has it accepted? Okay? They may or may not be the same. Okay? They may be the same too. The initial algorithm I'll give you, they'll be the same, and we'll see what there's a problem with that. Okay? So now we have, so far we had one proposed phase and two overall. Okay, we had one proposed phase, then one learn phase, and the proposed was just one phase. Now we have two proposed phases and three overall. That means before sending the accept requests to the acceptors, it sends a query request. Okay, saying, hey, what's your state? Okay, what's your state? What's your state? And these answers come back to it, not to other people. They are not broadcast. Okay? So it gets an answer, gets an answer, gets an answer, and based on the answer, based on the state it gets, it decides what its next step is.
So this basically exactly what you're basically
Sorry, Nick?
It's basically exactly like the three-phase commit. But
So this is a form of three phases, but this is distributed. Okay?
like if you do a database in the cloud, it should be distributed.
Yeah, so this is, I mean, Paxos is an example of a three-phase commit that way. It's not often sold that way, but yeah, there's three phases. In fact, Lamport keeps talking about two phases because he's interested in the proposed phase. Okay, so he keeps talking of phase 1, phase 2. He doesn't even use the word phase 3 in his proposal, but there is a phase 3 of learners. Okay, so far so good. So pre-propose. Before you propose, it's like before you take a vote, right? So pre-propose and sends a proposed message to query the current state of each processor. Acceptor sends back latest proposal seen and last accepted value. Okay? And now it gets back a message saying this is the value. So the prepare message is associated with the callback in the proposer, which is the prepared callback. Okay? And the prepared callback should do now what? That's the challenge. That is the most difficult part of the whole algorithm, in fact. Everything else was following naturally, I think. But this is the part that I had to struggle with, that I struggled with. Okay? So Matt, your solution, your suggestion was that if there's a majority value, so let's go and look at the cases here, okay? So basically the goal, we don't know what will happen in this step, but what we want to, the property we want to ensure is that it doesn't propose a new value if it could override a learned value from a previous proposal. That's what we want to ensure. How we do that is going to be tricky, but this is what we want to ensure. Okay? So let's go and see what prepared is going to do now. The prepared occurs in phase 1. Okay? So it's going to wait for responses, right? Now we could say it should wait for responses from everybody, but that defeats our fault-tolerant system design. Okay? So we are going to wait from a majority. Okay? And so it gets some data from a majority of acceptors. And what should it do now? So I think I've got some cases here. Here's one case. Some proposal has seen a higher proposal. Okay, that's one case. The other cases are that the acceptors have all seen lower proposals. Okay? But no acceptor has accepted the previous proposal. It has seen the previous proposal, but has not accepted it. That could be also a condition. Okay? So that's another case. We're going to try to divide this into multiple cases so that we can figure out what to do in each case. Okay? Or what Matt mentioned. Majority responding acceptors have accepted some previous proposal. Okay? At least one acceptor has accepted some proposal, but no majority value in the acceptances are received. Okay, so it doesn't know about a majority value. So let's take care of each case individually. What should it do if some acceptor has seen a higher proposal?
Just out.
Do nothing. For safety or for progress? For progress. If it sends a proposal, it's going to be discarded anyway. So let's just ignore it. Okay? So let's consider the easy case first. Proposer abandons proposal if it learns about a higher numbered proposal. Okay? So this is progress rather than safety condition. How about no responding acceptor has accepted a previous proposal?
Fine to proceed. Yeah, it's fine to proceed.
You
You can propose.
can propose. Okay. So proposer sends its proposal and value if it does not know about the previous accepted value. That's what you're saying, right? So no previous proposer, no acceptor has accepted the value. It just says, okay, finally I get to choose my value. Won't work. Think of two concurrent proposals. Right? This is why things are distributed systems is difficult. Oh, sorry, what did I do? Okay. So we're considering this case, and seems intuitive that we should accept this proposal, but we have to think of concurrent proposals, and 1 and 2 can both find this condition and propose their values, VP1 and VP2, with P2 being greater than P1. Okay? A majority of acceptors could get and accept VP1 first and then VP2. Back to square one almost.
Yeah.
But nice try. What really happened? What went wrong? Okay. Guys, I didn't realize we've been here, 1 hour and 15 minutes? So as you have to leave, do so. I'll stay till semi-synchronous replication till there's one person, and hopefully this will finish soon. But we are getting to it. Okay. So what went wrong here? The proposer sent, I think I've got something here. Proposer went and read a state, but that state kind of changed underneath it before it could use the state. It's like the test and set problem. You tested the value, but by the time you go to set it, some other guy interfered. If you guys can figure out what the next step is, fantastic. Yeah.
Could it be like for the acceptor, you will have like a current queried by some proposer, and if another proposer comes in and I'm currently queried by somebody else, go away.
So basically, so far the query did not have any side effect. It was a get.
Yes.
What you want to do is
Locking somehow.
lock it and say, learn about me. I exist. Okay? I'm not only going to tell you, I'm not just going to query the state, I'm going to tell you what proposal number I'm going to choose next. Okay? Store that proposal number.
Yeah.
Who's storing the proposal number?
The acceptor. The acceptor gets to know about the proposal number before the proposal.
Okay, and then who locks? Who?
So somehow that proposal number will be used to lock out other proposals.
Okay.
That's the key. So what I'm saying is here, there are three things. We are trying to get the acceptor state. That's a get. We are trying to set a proposal number and propose a new value, an acceptor. Right? We want to do 2 sets and 1 get. We can't do all 3 in one go because that would be one phase. That means we are asking you to accept a value regardless of what's been done before.
Yeah.
So we are going to have to make the write of the accepted value in a separate phase. So the get and the first set are done atomically. Okay. So cannot do all 3 atomically as a result of get affects proposed action. So can do get of acceptor set and set new proposal number atomically, which is exactly what Nick was saying. Okay. So my pre-propose sends a prepare message. So it's not a query. It's not called a query operation. It's called a prepare operation. It's saying, hey, prepare yourself for me. Okay. And by the way, also, tell me what you know. So let's exchange some information. Okay? and each acceptor sends back the latest proposal seen, the last accepted value, and then updates the last proposal number seen. Okay, we are there, guys. We are almost there.
But this is cheap.
Sorry.
How do you enforce this to, like, how is updating the last seen proposal number going to lock out
Okay.
income?
How is the last seen proposal number going to lock out?
Another concurrent.
Do you remember what the algorithm acceptors were following? Whenever they get a proposal number and value, what criteria do they use to decide whether a proposal is accepted or not?
Maybe the proposal number is higher.
Higher than what it already knows about.
Yeah.
So always, the last scene will always be the highest.
The last seen, yeah. Okay.
So even higher or something.
Okay. So we aren't quite done yet.
Okay.
Okay. This is why it took me so long to make these slides, also, guys. Not only I had to think. I had to fill in all the gaps that I didn't quite see, I didn't see filled in the paper. Okay. So can this problem occur now?
Yeah.
1 and 2 can both find this condition true and propose the values VP1 and VP2. Could a majority of acceptors get and accept VP1 first and then VP2?
Yeah.
Because now the proposing of it is different from the accepting of it. So even if both values are seen, that's fine. They haven't accepted it yet.
So you're saying this problem will still occur, or this problem will not occur now?
It can occur.
It cannot occur because, tell me again?
Because these are just the proposals you've seen.
Yes.
You haven't done the accept.
You haven't done the accepts.
The problem is the majority of acceptors could get an accept from VP1 first.
By the time the accepts occur, you have seen the proposal numbers.
Yeah.
You're going to pick one or the other.
Right.
At least one node has seen both.
Oh, okay. Yeah.
At least one node has seen both proposal numbers.
Yeah.
And it'll pick one and not the other.
Yeah.
Okay? Okay. So we're getting there. Okay, what happens if this majority responding acceptors have accepted some previous proposal? Max first. What should we do now? Abort, right? I cannot tell you how long I thought about why Lamport did not suggest this. And finally, 2 days ago in a walk, I figured it out. So that's not what you do.
So this is counterintuitive also.
It's counterintuitive. So he jumps over one step in his derivation, and that's the one step I'm spending a lot of time on. It's counterintuitive till you see the solution, then you say, of course. So this was my thought, and proposes no value if it knows majority has already accepted the previous value. And by the way, just because Lamport doesn't have this in his solution doesn't mean the solution won't work. He just provides you with something that's sufficient to reach consensus. He's not saying something else is not also sufficient. He's not saying it's necessary. But being as smart as he is, I was wondering why he didn't consider the more obvious thing that I'm considering. Right? So think again. Can you guys? Yeah.
The learners can change their mind, right?
Well, no. One of the invariants in our algorithm is that learners never change their mind.
Oh.
If that invariant is being kept true, so the question is, what should we do to keep that invariant true?
Gotcha. We've gone over
Yeah.
a lot of different kind of.
When I finally show you the algorithm, it'll be so simple to remember and even understand. Simple to understand, and I think simple to remember also. Okay? Remember, you're sampling majority and not the whole thing. And we don't know, that everybody knows what the majority is. We know what the majority is based on our sampling, but messages may still be being propagated in the system. Okay? So this is my argument. One's prepared. So when I say one, sorry, I really meant I've got some typos here. I meant this is proposal 1. Okay? I'm saying this is proposal number 1 also, I think. So one's prepare phase has locked out, is going to prevent certain values from being accepted now. In particular, this majority value that it has discovered, that majority value may still be percolating in the system. And this proposer has gone and locked those guys out from accepting those values. Okay? So it might have prevented some more acceptances from happening because it had the side effect of initializing the proposal number. Okay, that's all right. We know there are majority of acceptances. They'll finally make their way through, but somebody in this majority may die. In the node that you sample, somebody may die. So even though there is a majority of potential acceptors in the system that can accept the correct value, if the value percolates, that majority is not being used. Okay? So if some of the nodes in current majority die, some learner nodes may not get consensus value even though majority of nodes are alive because they've been locked out of getting that value.
So if we have the potential nodes majority gets through to the acceptors and are accepted, then we know we have consensus.
If majority of
So you're saying if some of them die, the majority could be lost. But if
yes, the majority could be lost indeed.
right.
The majority, some nodes are lost. I've got one majority. There are many majorities possible, right? If some of the nodes in my majority die,
A new majority possibly take over.
so we want a new majority to go and tell the other nodes that don't know about the value. But I may have locked out some of the nodes that have yet to know about this majority value from accepting the value because my prepare had the side effect. Okay. Again, I think it's right, but I haven't seen this argument in Lamport's paper, but I believe it makes sense, right? Once I describe it. If I had time, I would have constructed the case also, but I was just, these slides were just in time for the class. Okay, but it follows that you've locked out somebody. Okay. So want consensus value to propagate to all acceptors for fault tolerance. We want that property. So what can we do now? We don't want to play spoil sport and propose our own value. We want the old value to percolate so that it is learnt. So what can we do? This is again, maybe it's not obvious, but when you see it, it's a brilliant step. So the proposers that are locked out are the acceptors that are locked out are the ones that are wanting my value or higher. Right?
Higher or lower?
Or higher. Once you go and put a proposal number in an acceptor, it will accept only values that have proposal numbers higher than the one it knows about.
Right, so if it's locked out, shouldn't it be lower?
Locked out.
Oh, never mind. Yeah.
Yeah.
You're right.
Right?
Okay, I don't know if this makes sense, but maybe you can update the proposal to the acceptors, like
Brilliant.
it makes sense. Okay.
Please, when you go and fill in your class participation, please mention this. Exactly. You make me so happy for having said that.
It was over my head. I didn't even know what I was saying.
Well, you said right. That exactly. When the proposer is going to say, okay, these acceptors will accept my value, but anything that I sign, I will sign an accepted value. Okay? This way I'm not playing spoil sport. plus I am making sure that the value percolates. Okay? Proposer reproposes majority value as its own value. Okay? That's what we're going to do. It adopts the value. Like it?
Oh, okay. But then, so you do essentially two proposals, right? So you repropose the majority value you get, and then you propose the new value you want.
It can be true. The same value can be proposed not once, twice, thrice, n times.
Oh, okay. So it's just like this, in this proposal, we're not proposing the
Original value. We're not proposing the original value, we're proposing a new value.
Okay.
Okay? Cool? Hey, it's derivable. You just proved Lamport is right. It is derivable from the distributed properties of the property of distributed system. Okay. So now once prepare phase cannot prevent nodes from accepting the previous majority value. Okay?
Okay.
And this second problem won't occur either. Okay? Okay, we got one more case left. We did not see a majority value, but we saw some accepted value. Okay? In case 2, we saw no accepted value, so we proposed our value. We proposed our value. Case 3, we saw a majority value. Now we saw some values, say 1, but we didn't get a majority, or we may have seen multiple values, but there's no majority value in the replies.
Yeah, but it could just be that our sampling didn't get.
So it could be that a sampling hasn't got everything.
There is actually a majority vote, but you didn't sample.
So that's the question. There might be a majority vote that's about to occur or has occurred, and we don't know. Or
Oh, okay.
it could be there's no majority vote. Either of these two cases can occur.
Yeah, but either way, you don't know what's going on.
So you don't know. So what is the safer thing to do? Yeah.
You just do the same thing.
You can just do the same thing. You are on a roll. You can just play safe. Okay? Proposer reproposes the highest accept proposal number as its own.
How do you do that?
So it figures out what value was associated with the highest.
Yeah. Same thing, okay.
I've got a typo here. Proposer proposes the value associated with the highest proposal number as its own value. That's what I should have been saying.
Highest accepted proposal? Hold on. So you meant to say accepted.
Okay, what I really want to say is proposer proposes from the prepared request whatever proposal numbers it got, which were the highest proposal numbers it got. Okay, some of those proposal numbers were associated with accepted values. Some of those proposal numbers were associated with no values. It finds the proposal number, highest proposal number, with an accepted value.
And then
Proposes that.
Okay. Cool. So you gotta retry a bunch of times, basically?
The value with the highest proposal number may or may not become majority value. Okay, we don't know what is the case. So like Ramon said, just be safe. If it does become majority value, then prepared phase may have locked some nodes from accepting it. Okay, and we know there's a value already. So, we just want a common value. We don't want our value necessarily. Okay. So we're done. We got the algorithm. Okay. Proposer abandons proposal if it learns about a higher number proposal. Proposer proposes no value if it knows majority has already accepted the previous value. No, sorry, this is not what we do. So I've got the second thing should have. No, this is not. Proposer proposes its value if it knows majority has not accepted any value. So sorry, try to correct this. We've already gone through this step. I was trying to summarize this, and I copied the wrong box from one of the previous slides. So there has to be some situation under which we will propose our value, right? The second box is that situation. It is the situation when we got all these replies back and we saw no accept value.
Oh, yeah.
Okay? So sorry about this, but I was, like I said, copy and paste I meant. Okay? And reproposes with the highest accept proposal number as its own value, which may also be majority value. Yeah.
Yeah, so if going back to our case, box 1 would be case 1, box 2 would be case 2, and box 3 here would be the case 3 and 4.
Yes, box. The case 1 we saw earlier, same case remains. This is the middle, box 2 is the case 2, and the box 3 is combining, as Ramon said, the two cases.
Okay,
Okay, so we are summarizing now. We've got, I hope I've got things right here. So a proposed message sends a prepare message with proposal number to query the current state and set its proposal number. Now, when you see this now, it's not so hard. I'm summarizing the whole algorithm. I'm sort of doing it all over again, okay? So proposed message sends a prepare message with proposal number to query the current state and set its proposal number, right? Acceptor, it sends back, acceptor has to respond in two phases. It sends back latest proposal seen and last accepted value and updates last seen proposal number, right? Phase 2, again I've got the same mistake in the second box, but phase 2 we just saw. And acceptor accepts a proposal if it has the highest proposal number it has seen so far. Okay, so the algorithm, if I was just to have described it and not derived it, would have taken me 5 minutes or less. Okay, but we went through this process. And then a learner picks the first proposal that has a majority acceptances, and it knows that any other proposal will also have the same value. Okay?
Other learners.
Basically, the same value may be learned multiple times, but they'll all be the same value.
Yeah.
Okay? Okay. So, getting this right in my head took me some time. I can't even tell you how long it took me to make this. I started making these yesterday. I literally didn't sleep in the night to get everything done, all the animations and everything done. Okay. So, let's consider what's happening here. Propose 142, propose 229, the same case we've been considering so far. So prepare 1, prepare 2, start, right? Prepare 1 goes to node 2. What will node 2 respond at this point with? What you see on the left is the last value I've accepted and the last proposal I've seen. I can have a last proposal seen but no value accepted.
Yeah, so choose proposal box would have been 1 if the error goes through.
So at this point, what will this 2 reply with?
Oh, 2 question marks.
Yeah, very good. It says, hey, I'm sending this extra 1 back saying that proposal number 1, by the way, I don't know what, so I'm putting the proposal number before that just in case these things get confused. But we don't need to send the proposal number back because it knows, but I'm just sending this back in case we have 2 outstanding prepares, for instance. Which shouldn't happen, but it happened. There was a bug that I discovered this morning, which took me a little time, and I'll show you what the bug was. Okay, so, and it goes in, like you said, updates 1. Okay, says that I have seen 1 now. So far, so good? Now 3 goes and sends a request to 2, and what will it get back?
Question mark.
One question.
2 is the number, proposal number. I guess it's a little confusing.
Oh, okay.
It gets back its proposal number with 1 question mark, and now this is 2.
Isn't this shouldn't it be question mark and then 1?
Oh, sorry.
Yeah.
Okay.
Yeah, I mean,
We don't know what the order is, right?
It's not specified, but
Yeah, so let's assume. So far we don't know what the order is. Let's assume the proposal number comes first
okay.
and the value comes next.
Okay.
Okay? Good? Now, the accept occurs at node 1 also, right? Prepare request occurs at node 1 also. And node 1 goes and says, no, I have seen nothing before. So that's what its own answer is 1 question mark question mark. Okay? This number, node 1 is accumulating all the responses. It's got 2 responses now. Its own response
Yeah.
and the response from this guy.
Yeah.
So it's ready to
You-
accept,
yeah.
right? And there's no previous value. So it updates its value, updates its proposal number. Okay, I guess I haven't gotten to that first so far. 2 does the same thing at its site. It says, okay, I've seen 2 and I've seen nothing before.
Yeah.
Okay, so that's a 2 question mark question mark. And it updates its value. Okay, so it's like there are multiple actors. I was wondering in what order to stage the plays. Which one? When you have multiple actions occurring in a movie, you don't know which sequence to show at one time. So now we can do accept at node 1. Okay, and we can accept our proposal number because there is no accepted value so far. Right? So it sends the accept request here. Will the value be accepted?
No.
Because it's seen 2.
Yeah.
Okay. Will it accept its own value?
Yeah.
Okay. So that's what this 142 says. It says I accept my own value. Okay. So it's got 1 acceptance. It's not quite ready to go and say accepted so far. It's not quite ready to go and tell the learners that the value is accepted. Okay? And it goes and changes its value and says, I have accepted 42. I have, but I haven't got enough acceptances, so it did accept its own value, so that's 142. Okay? I could have shown 142, this vertical arrow as a horizontal arrow, that would have made more sense, but that would just take more horizontal space, and I was running out of space. So I'm sure that is the vertical arrow. Okay, it goes and sends its acceptance to other nodes saying, hey, I know about 142. That's accepted. I've accepted this value. It hasn't learned the value, but it has accepted the value. Right? So each acceptance is broadcast to everybody.
Also, like the acceptors are talking to each other too.
Yeah, because now they're talking as learners. It's saying, any learner, I accepted this value. As a learner, I have not accepted this value. But as an acceptor, I've accepted this value. Right?
Oh, okay. Okay.
Right? Because as a learner, you have to go and decide on a consensus value.
Yeah. Yeah.
That's when the accepted method is called on you. Okay? So, and that's when alright. So, it's counting the values, acceptances that is received, and it is not declaring consensus. But it tells the world that, okay, my value is this. Okay? Now, number 3 has got two prepare requests back. None of them has specified a previous value. Okay?
Yeah.
2 question mark, 2 1 question mark. So it goes and says, let me propose my value. Right? It accepts its value, just as number 1 accepted its value, it accepts its value. Okay? It goes and says, I accepted this value, 29. It sends this, and it also sends the accept request to node 2. Node 2 says, oh yeah, I've been waiting for you. Okay. I've been waiting for proposal number 2. So it goes and says, I accept 229. Right? And it accepts 29. It goes and says, I accepted 29.
Yeah. And then,
Right?
okay.
And it sends its acceptance to node 3. Node 3 says, aha, I've got 2 acceptances. I'm going to learn. In the meantime, it sends its acceptance, individual acceptance to node 2. It says, aha, I will learn. I'll learn this value.
Yeah.
And I don't know whether my slides show this or not. I'll click. But just in case the slides don't show it, these two acceptances can go to node 1, which can say, oh, I learned a new value too, 229. Even though it accepted 42, it learns 29. Right? Because these messages are being broadcast to everybody. So let's see if I have that. Yeah. These two acceptances go there too. And it says, I learned 229. I accepted 42, but I learned 229. Okay? Now you can see why it took me so long. Okay. So this is one case. But you get the general idea. So what happened there was each prepared phase occurred before any accept phase. We had prepare, prepare, accept, accept. Right?
Yeah.
Let's now try to have prepare, accept, and repropose. We haven't seen that. So let's see that happen. That was my goal, to create this particular one. Okay? So I send my value. I get back one question mark, question mark. This guy updates his value. I go and prepare myself. I update my value. This guy does the same thing. Okay? So far, it's the same set of actions. Now what happens is that before the accept occurs at this point, okay?
Wouldn't just be a same case.
Yeah.
Yeah, it's a bit too forward. But
Let's see what happens. Maybe I copied this slide over, and I hope I didn't delete my. I did have it working at one time, but let's go and see what's happening here. It sends its accept request to other people, and
okay, objective.
it proposes 42, just 142. This guy's accept request occurs. So 2 has committed himself, but before 2 went and prepared itself for its value, it sends back the old value. It sends back saying, okay, sorry. Okay, let's just see what happens. Okay, I'm not sure. So sorry, it sends it to the request, and it gets 2142.
So is that the black arrow is the prepare?
Okay. Now I know what's happening. Okay, so what's happening is 2's prepare request goes to 1, right?
Yeah.
And response comes back as 2142. Okay.
Yeah.
So this case is the same as before, except that number 3 is lazy. Number 3, when after it got the majority, it said, "Oh, I'll take my time out accepting." The accept thread took a while to execute. In the meantime, it learned about 1's value. Right? Just because you're waiting for majority doesn't mean you might or not end up getting everybody. So yeah, sorry, I'd forgotten what I'd done here. So the same case as before, except that we are now waiting. We have delayed 3's accept to a later time, to a time after which it sees 1's accept. Okay, and because it saw 1's accept, it proposes 242.
Okay.
And now, of course, it will get accepted.
And then who reaches? Okay. Yeah.
Because
Yeah, because
nobody's accepted any value. It just delayed. The problem was that it got 3 responses rather than just 2. And even in the previous case, it might have got 1's response back faster than 2's response. So even in the first case, the majority might have involved 1's proposal. Okay? So it proposes just because it's accepted. So that's what happens. Okay. Let's look at what's happening here. 1 prepares, 1 sends a prepare request, 1 also prepares, updates itself, sends a request, gets back a response. This value becomes 1. It sends this accept phase. It does this accept, accepts it, sends this value to 2. That accepts it because it has not yet got a prepare request from node 3 so far. Okay?
Now you can.
Now it's got a majority, right?
Yeah.
In the meantime, and this guy also, number 2, also learns about, accepts 142. Okay? So this is the response to the accept request. And in the meantime, then, okay, so the prepare request arrives from node 3, and it says, oh, it's 142 is the accepted value, right? So now there are enough accepts in the system to have a consensus, right?
So you drop the
And 2's own thing occurred earlier, okay? So it updated it to 2. Now 3's request goes here. It gets back to 142. Okay, so now it's got 2 142s. Okay, so we could do as what we had talked about earlier in Matt's case, that we could just say, oh, I'm not going to propose any value.
Oh.
Right? We could have done that.
Oh, okay.
There is now a majority going around. We just have to wait for the messages from 1 to go to 2, 2 to go to 1, and there'll be majority. But, and this value comes here. Okay? This value comes here, so there's a majority here. But this particular node 2 dies. So if that message had come, there would have been majority. But node 2 dies now. Right? So I'm saying, had the animation showed you that had that message arrived at node 3, there would have been a majority, but node 2 has died now. Okay? And now we don't have acceptances, 2 acceptances of 42 any longer coming to us. We have to make sure that we accept 42 ourselves to get the majority. But we will not accept 42 because we've locked ourselves to 2.
So you repropose.
So you repropose. Okay? So we go and repropose ourselves. Okay? Okay, here's the easiest case. Prepare 1. But before prepare 1 reaches node 2, prepare 2 reaches node 2. Right? So this one gets 2 question mark, and this one gets 1 2 question mark, and so node 1 got its own 1 question mark. Okay, but it didn't get majority of responses from prepare. So now it gets 1 2 question mark, and what should it do now? Nothing. Okay. So no accept. Okay, so 229 accepted here, accept 229. Okay, now finally consider this situation. This is something that Lamport actually does consider. Prepare 1, prepare 2 occur. Prepare 1 goes to node 2. Right? Now node 2 will not accept any values from node 1. No, because, sorry. It changes it to 1. Now 3 proposes. It changes it to 2. Now node 2 will not accept any more proposals from node 1. Right? The number is 2. My proposal number is 2. So I will not accept any value from node 1. Right? Nick? It's this.
1 propose 3.
Okay. So 1, this is what's going to happen now. So one goes and says, okay, I'm locked out, but it's got a timer running that is there any value accepted or not. And node 3 is taking its sweet time to accept a value.
Oh, okay.
So node 1, node 1 sends an accept request, and the accept request goes here, and is denied. So it goes in. It finds that message saying denied. So it puts a timer on, and no accept request occurred. So it did a prepare 3. Okay, prepare 3 goes to node 2. Node 2 picks up 3. Finally, node 3 decides to accept, but its value will be rejected by node 2 because this is thinking of 3 now. So when it goes in, it goes and does prepare 4.
Oh, so like, yeah, so you're locked out.
Okay, so there's just too much. The timers are too short here, too small. And it's 6:30 in the evening, so we can try to figure out this problem, or we can just look. So we're getting to it. Each replica could be okay. So, God, did I lose that slide? Okay, sorry. The reason I have the slide here is that we are assuming that proposals are going in increasing order now. Okay, I said earlier the proposals doesn't matter whether they're increasing order or not. Now I'm kind of claiming that the proposals have to go in increasing order. Okay, so how do we? So far what I'd said was that the proposal numbers have to be disjoint, and that's enough to make things work. But now I'm kind of assuming that the proposal numbers are increasing order. Yeah.
If for some reason the proposal numbers are not in order, you can set logic so that only if it's increasing you can propose it?
Actually, the system will work just fine if they're not in increasing order. It'll just keep rejecting certain values. It's just that we've got this pesty, this proposal that keeps proposing newer and newer values. And to accommodate that person, we say maybe we should have higher numbers. But the system of safety is guaranteed no matter what happens. Okay, so the question is, how do you get proposal IDs and how do you get them disjoint? And one approach was you just give them different sets. If you give them different sets, there's no guarantee of there's no guarantee that newer proposal numbers will be more than previously seen proposal numbers.
Yeah.
Right? So reproposals.
Might not be accepted.
Right. So we can have each replica keep track of known proposals, and ID of new proposal is one more than the known proposals. Okay, we could try to use this logic, but now we can come up with two proposals, two concurrent guys coming up with the same proposal number. Okay, so we could put our ID in the proposal. Okay, we could make the ID the higher order bit. If you make it the higher order bit, then all proposals from one side will be higher than all proposals from another side, even though some may be later proposals. Okay, so we will make the ID the lower order bit, and the ID was only used to resolve conflicts. So that's what we'll do, and I've got it. This is essentially what I do here, the code that does this. Okay. So ID of proposal made by replica will be unique and larger than the IDs of proposals it has already seen. Okay, how to avoid live lock? Okay, and the answer is very simple. Let all proposals go to a central proposer, and this way we won't have two proposers competing with each other. But we've got a centralized problem now.
Yeah.
Except that the answers don't come back to the central guy. The answers are going to the whole world. This is just to go and serialize the proposers. Okay? So if this guy dies, we won't have something bad happen like different consensus values. Okay? So all acceptors directly talk to learners. Majority value will be same. Okay? And like I said, we can use some other Paxos mechanism to achieve consensus about who the new central proposer should be if the proposer dies. Okay? Okay, we won't get into that. We can just use the ID number or whatever we talked about earlier. Okay. Similarly, what he suggests is that we have a central listener. All the acceptors send a message to one listener. That listener broadcasts messages to everybody else, so that we have two n messages other than n square messages. Right? So again, same problem, that you can have the central listener die, but nothing bad will happen. Okay, I have gone and taken so long to give you the argument. I won't go through this here, but in quotes, I've pretty much put the argument that Lamport actually uses, which fits into one slide. So at some point when you look at the slides, look at this. This might be more meaningful to you, because it's not going through cases like I went through. It's talking in more generalities. But he's got an implication from the bottom one to the middle one, and that's the implication that I just couldn't understand. So I had to go through the 4 cases that I went through. Okay. Otherwise, so I've got stuff from his paper in case I made a mistake anyway here.